Welcome back. All right, so we're going to prove our triangle's congruent using a triangle congruence postulate. We actually could do one of two different postulates. So actually, let me show you how to prove it two different ways. So it says side angle side, but we'll actually prove it two different ways. So we need to gather up some information here. Let's first prove it using side, side, side. And actually, we'll only take one more step, really, to prove it using side angle side. All right, so if we use side, 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 means we need to know the lengths of all three sides. Well, two of the sides in each triangle, they're pretty easy, right? Because they're horizontal and vertical lines, and our scale is 1. Right? So let's find the measure of AC here. Right? So AC, well, horizontal line from -7 to -5. Right? That's just, so we can use the absolute value of the differences, or we can even just write down the measurement. You know what? Yeah, I'll do both. All right, so -7 minus a -4. All right, so that's going to be -7 plus 4, which is the absolute value of 3, which of course is 3. All right, you probably looked at that and noticed that. All right, and so AB. On the podcast, I like to use the absolute value just because sometimes it's harder to count it, and there's times when it is harder to count, you can do it this way. All right, we have a vertical line. The x-coordinates don't change, just the y-coordinates. So we have the absolute difference between 5 and 0. So absolute value of 5 minus 0, that's just going to be the absolute value of 5, and that's just going to be 5. All right, so we have two of our sides. On the third one, we'll need to use the distance formula. All right, so I'm going to move this up here so that I can have the space for the diagonal line, right, for CB. Right, so for the length of CB, that's just going to be the square root of -4 minus a -7 squared plus 5 minus 0 squared. Right, so that means CB is, so that's just going to be minus and negative is plus. So that's 4 plus 7 squared, and then that's just plus 5 squared. Right, so that's going to be 11 squared. Oh, excuse me. Almost lost the negative there. 3 squared plus 5 squared. And that's just going to be 9 plus 25, which is the square root of 34. And that doesn't simplify. All right, so we're just going to leave it like that. All right, so now let's do the same thing with the other triangle. All right, so we need FH, or I guess we'll just call it HF. HF, which would, that's about a vertical line there. Right, so the absolute value of the difference between the y-coordinates, so the absolute value of 5 minus 2, that's just going to be absolute value of 3, which is 3. And let's do the same thing for FG. So the absolute value of the difference in our x-coordinates. Right, so I've got 6 minus 1, and the absolute value, that's just -5. Absolute value of -5 is 5. And now we will have to use the distance formula for our third side there, the diagonal side. So for GH, that's going to be the square root of 1 minus 6 squared plus 5 minus 2 squared, which would be 5 squared plus 3 squared, which is 25, plus 9, which is, hey, square root of 34. All right, so now let's do a proof using side, side, side. And then we'll add the one last step for side angle side. All right, for side, side, side. I wonder if I can move this down if they're stuck together. Oh, no, they're not. Let's just move that down. All right, so for side, 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 our first part of our proof, we have AC is equal to 3. we'll just put all the givens together. AC is equal to 3, and AB is equal to 5, and CB is equal to the square root of 34. Actually, I shouldn't say givens. Those aren't our givens. Actually, you know what our givens are? Not that. That's actually step 2. Because technically, we weren't given that information. Actually, the only thing we were given was this. Triangle ABC and triangle DEF. Oh, excuse me, FGH. So used to DEF. Now we have an FGH. That was technically the only thing we were given because we actually found this in the rest of the information. Right? So for number 1, we need to write in triangle ABC and triangle FGH because the one thing we were actually given were the 2 triangles, right? That's how we knew where the points were. We found this information, well, we found 2 of it, right, just by taking the difference, the absolute value of the difference, but we'll just use distance formula because we could have used the distance formula for all of them. And likewise, HG is equal to 3, and FG is equal to 5, and GH is equal to the square root of 34. And actually, if I want to make this one step, I could get rid of the 3, and we'll just call that one step because it's got the exact same reason. We got that using the distance formula. So now that we know the lengths of everything, we know that AC is congruent to HG, and we also know that AB is congruent to FG, and we know that CB is congruent to GH. So there should be congruence marks there, right? And the reason we know that, this looks like CH, and that's supposed to be GH. Congruent figures have the same measure. Trying to squeeze it in the spacer so I have a little bit of space left for siding on side. Same measure. And now that we know that 3 pairs of corresponding sides are congruent, we do know the triangles are congruent. We know that triangle ABC is congruent to triangle FGH. And we know that because we use side, 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 triangle congruence postulate. So I do want you to write both of our proofs here. You can always add some paper if you need it, but I will tell you that it's going to be a question on a upcoming test. So it'll probably be a good idea to have some notes on this. So we actually only need one additional thing to be able to use side, angle, side. We need an angle. We know all 3 sides, but one angle should be the angle that we find. Do you know which angle I'm referring to? Is there one angle that we know the measurement, we could easily find the measurement of? Well, if you're saying angles A and angle F, you're right. Right? To do that, we need to show, so the only angle you can find on a coordinate plane is a right angle. Right? I'll put that in there too. Only angle measure you can find on a coordinate plane is a right angle. That's the one you can find. All right, and we do appear to have one right angle. We just have to show that the 2 sides that create that angle are perpendicular. So let's find the slope. And we don't even need to use the slope formula. I don't think we need to. Right? So this is going to be for side, angle, side. Right? We're going to add just one more thing. And the one thing we need to have is the slope of our, the sides that make up angle A and make up angle F. Right? So we need the slope of AC. Right? Well, that's a horizontal line, so that slope is 0. How about the slope of AB? Well, that's a vertical line, so that slope is undefined. And how about the slope of HF? So M there stands for, we're using it for slope, right? I don't know how else to write slope as an abbreviation. All right, so we'll find the slope of HF. All right, well, that's a vertical line. That's undefined. And the slope of FG, that's a horizontal line, and that's 0. All right, so now we've got the slopes of our lines. All right, remember, horizontal and vertical lines are perpendicular. So we've got horizontal and vertical lines. Okay. All right, so I think we can start our proof here. We are going to start our proof with the same first step, and that is triangle ABC and triangle FGH, because somebody had to give us that. Right, so that one thing, if I move this out of the way, just a teensy weensy bit, the ever so teensiest bit in here, just so you can see it. There we go. So step number 1, that is given. Right, so step number 2, we're going to need AC. And we're going to need AB, but we do not need the other side. So for this particular proof, we've said that AC is congruent to a, well, we're going to say it anyway. AC is going to be congruent to FG, and AB is congruent to FG. Right? So there's our two sides, because our angle we're using is right in between them. So there's no point in even listing the other side because we're not going to use it. All right, so we've got that, and may as well list everybody here that we do need. HG is equal to 3, and FG is equal to 5. All right, so that part there, well, we can still use the, say, distance formula. We kind of did a modification of that by just taking the absolute value in the one coordinate that changes for a vertical or horizontal line, right? And so now that we've said that, we can say that AC is congruent to HG, and AB is congruent to FG, and it's the exact same reason over here, and so there's not a lot of space. All right, so let's just put for 3 here, let's just put the asterisk. We're filling in the exact same reason. All right, we're going to say one other thing. We're going to say that our angle A, actually we're going to say 2 more, 3, actually 3 more things. But angle A and angle F are right angles. Right? And how do we know? Well, what makes right angles, right? So perpendicular lines create right angles. I should have used my space better. Or meet at right angles. I used a lot of space for the one proof. I gave myself an easy bit of space for the other proof. All right, but I hope I got enough room for my transformations. Move it down just a teeny bit more. All right, so now that we've said that, maybe I should have just done the one. It's good to see both of them because I'll ask you to be able to do both. Now that we've said they're right angles, we can say angle A is congruent to angle F because I'm going to move this step, and we're going to abbreviate even that more. Distance formula, same as before. So then for 3, that was the same step on the other side that we just can't fit in right over here. So we don't have to write it twice. And then if we move this one over just a little bit, so 3 goes down here. Oops, poor 3. It's all in pieces. See if we can squeeze everybody in. There, I think we can do it. All right, so 4 perpendicular lines create right angles. Number 5, angle A is congruent to angle F. The reason there, all right angles are congruent. We almost got it. All right angles are congruent. If I had more space on this side. And then the last step, the last little step, you know, I wonder if I just clone this page and we'll do the transformation on the other page. Oops. And has it been created? It's thinking about it, and then we can move that last statement that's in my way. There we go. All right, let's get rid of this for a moment. Right? And so our last little statement there, now we've got some space. I don't know where to, here. I'm just going to move some of this over so that this is not going diagonal like that. All right, so we'll just fix it up over here, move this over there, have this was same measure, and then the triangles are congruent using side, side, side. There, now we have some space. Feels good to have some space. Now that we're nearly done. And I think that's probably good enough. I think you can see it. Just trying to make sure you can actually see it. All right, so, and not have to write. I'll write that over again. Well, this is giving you time to catch up to me writing, right? So this was 3 here, oops, and then 4 is just going to go here. There we go. And, there, doesn't that look so much better? Now you can actually read it. We'll still leave the 3 as the asterisk. So angle A and angle F are congruent because all right angles are congruent. They all measure 90 degrees. And now that we know this is congruent to this, we can say that triangle ABC is congruent to triangle FGH. And the postulate that we used was side angle side. So here's 2 ways to prove the triangle is congruent. And now we're going to look at, so side angle side, triangle congruence. We're going to look at one more way to prove the triangle is congruent. Whew. There we go. I should have figured out my spacing a little bit better, but now I think you could read it. Right? So the other way on a coordinate plane that we can prove triangles congruent, remember, is to show that there's a sequence of transformations. All right, so let's find that sequence of transformations. This one's a little bit tricky, I'll tell you. And any day now. Oops, well, remember we had all the ink here. So we'll just erase all of this. Well, I'll erase some of this. It doesn't like to do that thing I always do in class where you make a big circle and you go bump and it all erases. No. I think it's too slow when I'm recording. There we go. All right, so we already proved it using a triangle congruence postulate. All right, so this was done. Let's use a sequence of transformations. All right, so notice they're not facing the same way. We need to move one of them, ABC or GH or FGH. I'll move ABC because that one's listed first. They're not mirror images of one another. They're kind of turned. So let's turn our figure by rotating. I like to rotate around the origin. All right, so for step 1, let's rotate And we're going one quadrant, so that's 90 degrees. 90 degrees, and we're going to go clockwise. And actually, let me also write in the triangle that we're rotating. That's triangle ABC. So we're going to rotate triangle ABC 90 degrees clockwise about the origin. All right, so remember the rule. XY goes to negative Y, negative X. All right, so if we look at our points, that means that negative 7, 5 goes to, we switch them and make now, oops, not negative Y, negative X. I believe I said negative Y, negative YX. All right, so we're going to switch them. And now, oops, not negative YX. I'm thinking 270. X negative Y, right? We're going to switch them, and the second one's going to become negative. And let's say we had the sign wrong. We didn't realize it. Well, when we go to switch them, we go, wait, they're both supposed to be positive. And now I just negated the one that's positive, right? So we would mess up, right? So, but if we just look at the coordinate plane, if we make a boo-boo, right, we can see it right away. All right, so if we flip the negative 7 and the 5, right, we'll have 5, negative 7. But we got to change the sign of that second one. So it's not going to be 5, negative 7. It's going to be 5, 7. Right, and then B is negative 7, 0. Right, so that's going to be now 0, 7. And C is negative 4, 5. So that's going to be 5, 4. All right, so we'll graph that. So we have 5, 7, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Yeah, that's nice. All right, we'll just put there's 7. All right, so your page is going to be a little crowded. Negative 7, 0. So, oops, becomes 0, 7. So we're on 0 and 1, 2, 3, 4, 5, 6, 7 up there. And then just make sure I didn't look at the wrong, nope, okay. Got to make sure I'm looking at the right coordinates. And then 5, 4. 2, 3, 4, 5, 1, 2, 3, 4. All right, so now here's our triangle. All right, a little crooked there. All right, so so A is 5, 7. So this one is A prime. And this one is B prime. And this one is C prime. All right, well, it's closer. It's still not in the right spot. What if we do another transformation? I don't think we can do this in one, right? Because we're not lined up. Right? We're not exactly mirror images with one another, but they're sort of mirror images, right? They're just not quite in the right spot. So what if we reflect over that line? Okay. So we're going to reflect over 1, 2, 3, 4, y equals 4. Once we do that, our triangle will look like this. Right? So it's going to be 1, 2, 3, 1, 2, 3, 4, 5. Right? And here will be our triangle. Right? So A prime won't move anywhere. This is going to be B. So this will be B double prime, I guess. And this one will be C double prime. And now we have only one more transformation. We don't even have to draw this. Right? We want to map C to F and B to G and A to H. So we have one more transformation, and that's a translation, and we want each point to move 1 to the right, oops, and 1 up. And there we go. So now 3 different ways to prove these triangles are congruent, through transformations and through a triangle congruence postulate. So these 2 triangles, definitely congruent. That's the end of this podcast, and bye for now.